I've always had the impression, Professor Campbell, that your message tends to be a little polarizing. People that I've talked to, either
Oh,
they
okay.
they accept it and they live by it, or they just reject it. And
That's true.
I wondered, why is that? Why are you such a controversial figure?
Yeah, I wish I knew.
You're listening to the Foundry Talk podcast with your hosts, Nate McLean and Perry Merritt. Take it away, boys.
Well, welcome back. My name is Perry. As always, I have with me my partner, Nate. And Nate, when we first started this, I remember talking about who could we get onto the podcast? Who could we get to talk to us, right? And one of us throughout Professor Campbell is a name. And we both, I remember laughing, thinking, yeah, if that would only be possible, it's sort of like the apex of guests we could get. And here we are today with Professor John Campbell. I think I speak for the two of us. We are both honored and just humbled to be with you, and looking forward to the conversation with you. Thank you so much for being with us. I wanted to ask you, Professor Campbell, you and I haven't talked for quite somewhat time. What have you been up to in the last, couple of years? It's been a while since I've talked to you.
Oh, okay, there's a challenge. I'm very good at forgetting what I've been up to, but let me see if I can think. The really big project I have at the moment is a project up in the north of England, which I drive 5 hours up very often on a Monday, and then I drive back very often on a Thursday. And the project is melting secondary aluminium, recycled aluminium, and we are getting rid of biofilms by treating the metal, and then moving the metal uphill using a pump to fill castings in a counter-gravity way. And it's been both exciting and immensely frustrating project, because if there's anything that can go wrong, has gone wrong. And that the frustration has been that the whole concept is actually very simple. Just to have a melting furnace, a treatment furnace, and finally a furnace to hold the good metal with a pump and to pump up. So you've got the three functions of the system, which are all linked together to work as an integrated system. And well, we're now in our second year, and we've got another year to go. Well, it is on occasions giving us sleepless nights, but we shall get there in the end. But it has been uphill, and when you think, oh well, we're only trying to do something rather simple, but when you come to do it, you can think, I can see why no one has succeeded with this project before, because it's on the limits of possibility. And so that's something that's more or less dominating my life at the present time. But we have a good team, and we're all working at it. We're going to succeed. It's just taking us longer, and it's harder than we imagined it would be. So that's the big project. I've got numerous smaller ones, and I guess I've been spending quite a lot of time on the latest books and writing papers, attending conferences. This is what, as an academic, you tend to do rather a lot of, because there's no other easy way to get your ideas out into the world. I used to pride myself as being the author of the world's most unread Foundry textbooks. But little by little, people are starting to read them, I think. And, it's gratifying to discover a Foundry that's found your books and actually doing something with them. So, there have been some bright spots in the last few years, and me discovering people who are quietly beavering away using good technology, which I didn't know anything about. So what else have I been doing? You've really put me on the spot, Perry.
Sorry.
Yeah.
Well,
Yes, I do a bit of supervision of. I've got just part-time supervisor of a student doing a PhD at Birmingham University, which is the university where I was and where I did most of my research on castings and on biofilms. So it's been pleasant for me to renew my contacts with the university, because I've been away from them for 20 or 30 years. And this is the trouble with getting old. You've got so many years behind you, it's a problem to remember anything,
I think it's remarkable. Accolade, whatever the word is. I'm younger than you. I can't come up with the words. Congratulations to you to keeping yourself active and keeping engaged. It keeps us all younger. So good for you on that.
Well, that's true. I mean, I go out of my way to exercise every day. I swim every day if I can. I try to eat sensibly, and so I try to do all the right things, and have survived so far. So maybe I'm getting some things right.
I suspect
I think
you are.
getting a lot of things right. Yeah, doing exactly what you need to be doing. So
Yeah, I mean, it's not like you haven't been active over your lifetime. I mean, for the Pete's sake, I mean, you even have the Institute of Metal Castings Engineers. I mean, they have named an award, the John Campbell
Oh,
Medal
yes.
in your honor. I mean, that's
Yes.
pretty remarkable.
Well, when they asked me, they said they wanted a high-flying, internationally recognized medal, and they wanted to name it after me. And my first reaction was, but I'm not dead yet. And and that's always been my view of the medal, really. But it has been a pleasure to make the award to a great string of wonderful people, including our friend Bob.
Yeah. Yeah. I mean, so, and in my opinion, what better way to honor somebody is before they pass, so they can participate in it rather than after they passed.
absolutely.
I make it a point to actually call people that I appreciate, and they've touched my life, or they've given some sort of contribution to me in my life. I just did it yesterday to thank somebody for taking me under their wing, mentoring me, even though it was an indirect mentorship. It was still mentoring. I wouldn't have been in DC if it hadn't been for Ron Pomeroy, taking me as a young Foundry guy, and going to DC to lobby for the metal casting industry. I wouldn't have been there at all if it hadn't been for him, and the graciousness of the Plain States AFS chapter to send somebody. So people, I think it's outstanding that they're honoring you while we get to experience life together. That's fun.
Well, yeah, okay. I hadn't looked at it that way, but thank you. Yeah, there are aspects of fun to it. Yeah, I agree. Mm.
Yeah. And not just that, but what about the honorees that are receiving the award? No better time to have it, and when they get to experience with you, that is
Mhm.
huge. I mean, for Bob, for example, that had to been a huge honor for him to accept that award, and you experienced that with him. That's incredible. I think that's awesome.
It, what's interesting is the reluctance of people occasionally to accept, and Bob was one of those. And so
Sure.
part of my job is a persuasion job to say, look, the world needs its leaders. We're all pack animals, and we need leaders. And
Absolutely.
this is the main argument as far as I'm concerned. Mm. Mm.
Yeah. So, but before we get started, get too in depth in the podcast, for those individuals that may not know who Professor John Campbell is, or may not hear as we go through the podcast and they hear the term biofilm and what that actually means, in for us metal casters and people in manufacturing that are melting some sort of a Newtonium alloy, turning it from a solid to a liquid form, and then back to a solid in a geometric shape that is re-engineered or used in a manner that is constructive and helpful for the human race. Can you explain to those individuals that may not even have a clue who Professor Campbell is? Also, what in the world is a biofilm? What that term means nothing to some people, and probably, to be quite frank, some of the people in metal casting industry, their eyes are going to cross over and they're going to go, I don't know what the hell a biofilm is. Can you explain to them what that is?
Maybe let me try. You see, when I came into the industry, the mantra, the words which everybody would use in the industry was, we've got to avoid the turbulence during pouring. Pouring has to be smooth. And there was something about turbulence which was very damaging to the liquid metals and damaging to your final casting. And frankly, no one knew why turbulence was damaging. And no, I was just one of those ignorant people. This is where I came into the industry. This is where I started. But there had been some research, 20 years of development funded by the British Admiralty on aluminium bronze for getting reliable ships' propellers and other ships' fittings. And they had funded the British Non-Ferrous Research Association, I say, for 20 years for them to do research. And they had come up with a rule book, a thick, large book, crammed with rules to observe to make good castings. So I got myself a copy of this book, and I learned how to do it from the book and then applied it. It was interesting because very often I would not get a good casting. There were still problems. The thing about the book was that your casting wasn't as bad as it would have been without the book, but it was a long way from being perfect. And because I became so frustrated with these residual problems in the casting process, I thought, and I was working in the industry at the time, I thought, I've got to do some fundamental work. I'm a physicist. I stand the best chance of finding the answer to this mysterious question. And, I've got to get to the university and do some decent quality research. And what's more, I have to get some students, and because the industry needs young people, which it didn't have at the time. So that was the the reason I got myself to Birmingham University, I went there as prof of casting technology, and we did 15 years of research with about roughly 10 students on average throughout those 15 years. So we had 150 man-years of effort went into trying to find the reason for the problem associated with turbulence. And as I say, one of the initial clues came from me with the Cosworth process of bringing the metal up to with the electromagnetic pump just to be level with the top of the casting table, and the metal would be sitting there beautifully under control, and then if you tweaked it, it would just jump a small way, and then as it fell back, it became a little mushroom shape and folded in itself as it fell. And that gave it a clue that maybe it was the folding over of the surface, because the surface was oxidized naturally. And the other thing, as a physicist, you think, well, what's the structure of the oxide? And of course, the underside of the oxide, if this is our oxide, the underside is in perfect atomic contact with the melt. The top side is dry, it's out in the atmosphere, and so you have a perfectly dry surface and a perfectly wetted surface, and you're folding two of these surfaces together, and whenever you do that, it always folds dry side to dry side. Always. It's a fact of nature. There's no way out of this problem. It always does that. So even if you get two splashes of two droplets hitting each other mid-air, again, their oxides meet dry side to form a double film, but which doesn't bond. Because so that if it doesn't bond, it means it's a crack. It will easily come apart again. So the bifilm is something that's folded in, or because of a droplet falling onto the surface, its oxide hits the liquid metal's oxide, always dry side to dry side, and so always giving a crack, and that crack goes in and then swims around in the liquid as a double film, and it's the two dry sides together never see any liquid metal. It doesn't even know it's in the liquid metal. And as soon as you tweak it with a bit of tensile force, it'll come apart. And they get inherited by the cast process, so that when we're casting steels and we make ingots, we are making, again, these double oxide films with the dry side to dry side. Our ingots are full of cracks, and when we roll them, we extend the cracks in the rolling process, and we start to develop a texture. All these metallurgical features are all bifilm features, so texture is another. And it's the reason why the forging industry grew to be so important. When metals full of bifilms were produced, we get a big block of metal but want to make an anchor out of it, and so you would forge it. And the bifilms now go along the casting directions, so that when the crack tries to break off an arm of the what do we call the anchor? See, I'm struggling for my words, and it's where old age is creeping up on me. But when we're forging an anchor, and it's got kind of spade-like features and the main stem of the anchor. All these things are carefully forged and elongated, and the elongated bifilms, the elongated cracks, mean that if now we get a crack trying to cross and trying to fracture the main stem of the anchor, it can't do that because it keeps being diverted by the bifilms along the length of the casting. So the texture which we'd built in by forging, it actually proved to be the real strength and reliability of the product. So that's just a curious feature of bifilms that have been with us for like hundreds of years, and that's why our forging industry was necessary to get them aligned. But the bifilms have gone on now, and what I've discovered is they cause all sorts of fascinating problems in castings. For instance, fatigue. The fatigue crack moves from one bifilm to the next, to the next, to the next, to the next. It's got small ligaments of metal which it has to break in some way, usually plastically deforms them or shears them, but then it's at the next bifilm and suddenly it can move quickly again to the next ligament of metal. And so fatigue is very much dominated by the presence of bifilms. And without bifilms, metals probably would not fatigue. And this happened, I've proven this with the Cosworth process when we were making our castings for the Cosworth Formula One racing car engines, that 50% of our engines failed on the test bed because of fatigue. They never got out onto a racing car. But from the day that I made the castings with my new process, whereby I had the ton of metal that we allowed to sediment and the bifilms to settle to the bottom, and then we pumped the metal up into a mold without folding over the surface once to make a bifilm. And these castings never failed again. Fatigue was eliminated. No casting ever failed by fatigue from that day on. So from 50% failures to 0 overnight when the new Foundry came on stream. So that was dealing with fatigue, but there are other things. Creep is, we don't have time to talk about creep now, but creep would also be solved. Hydrogen embrittlement is another process which depends on the population of bifilms and the hydrogen diffusing into them and blowing up. And you know this is the reason, because the surface bifilms close to the surface get the hydrogen first, and they blow up as blisters. So you can see the process operating in front of your eyes. It's completely clear why hydrogen embrittlement occurs in metals. And the same goes for the other mysterious failure process, which we call, stress corrosion cracking. And again, the bifilms allow the corrodant to creep in along the pathways of the bifilms. They then dissolve away the ligaments and then onto their next bifilm. And all this can happen under a very gentle tensile force. Tensile stress. So with the tensile stress and the corrosion media, this is why this eventually the whole thing will come apart. It's very quiet, it's very slow, but it comes apart even under the most gentle tensile force. So again, we can explain stress corrosion cracking. So all these failure mechanisms which frankly, are not well understood. They're not well understood because people haven't known that the bifilm population is there in the metal. Whereas as soon as you know that, the explanation suddenly becomes easy and rational and in a way, obvious.
Sure. So, in the simple forms, I mean, so it's the oxide layer that floats on top of the molten metal being below, and
Yep.
whenever you pour that molten metal, get it from the either the furnace or the ladle into the mold cavity, you've got a turbulent flow, you've got metal floating, and you've got oxide film on oxide film sticking together, and it
Mm.
creates a crack that is nanometers in size, so small you can't see it with your naked eye, hard to see with an electron microscope. Is that accurate?
A lot of the bifilms are like that because many of them are formed during the turbulence of pour. When you think how long has the oxide got to build up on the metal before it's splashed over, and the answer is a few milliseconds. And so the oxide has got very little time to form, so it doesn't form very thick. It doesn't have time to form thickly before it's suddenly meets its opposing oxide film, and now there's no air can get at it, and it won't thicken anymore. So that's why most of them are so thin, but they're not all thin. And there are some which have come from oxide films sat on the ladle or from the furnace, and these can come along, and these can be very thick. So by the time it's millimeters thick, it's not a film anymore, it's a lump of oxide. But it
Yeah.
still meets its opposing oxide, dry side to dry side. So it still forms a crack, even though it's a chunk now, as opposed to a film. Yeah, so the effect
Yeah,
doesn't go
which is
away.
very challenging for us metal. Yeah, it's super challenging as metal casters
Yeah.
because you stop and think about the way that we have to melt, the way that we pour, the way that we have the furnace, and typically the furnace, which is not completely 100% true because there are electric furnaces, let's say for aluminum that you can melt. Thermtronics has some that you have an umbilical cord you can melt and pour from the furnace itself, which is the most ideal way of doing that. A lot of nickel, aluminum bronze, any bronze alloy per se. Um, I always like to melt those alloys in some sort of a crucible because I'm melting and pouring in the same vessel.
Mm.
So therefore, I don't damage the metal in my transfer from the furnace to the pouring ladle and then take it out and then go pour the mold. So I'm always the problem with that is like a 225 clay graphite crucible for copper based alloys. You're limited to about 500-pound pour. So you
Mm.
can't go pour a multi-ton mold.
Mm.
If you need to pour 4,000 pounds, well, guess what? We're limited on what we can do. And a lot of times, because of us metal casters, we don't have the capacity to pour multi-ton castings. We're having to transfer metal, say from a 2,000-pound furnace and a 1,000-pound furnace and a 500-pound furnace to get 3,500 pounds of gross weight to go pour a 3,500-pound pour weight mold.
Mm.
So in those processes, we're actually our worst enemy because we're damaging the metal. We're taking the metal from the 2,000-pound furnace and pouring it into the ladle, and then going to get the other two furnaces and damaging the metal some more.
Mm.
And then we ask the metal to do a really difficult job in a highly engineered part, is to go pour that metal into a mold and it to be structurally sound and not have the defects or bifilms that are in that casting. And it really depends on the alloy as well, because if it's a very fast freezing alloy, or you've got chills in the mold and that sort of thing, sometimes those things will help mitigate some of the unfurling or the opening up
Mm.
of those bifilms, to allow the air that might get entrained in that bifilm, which are known issues in metal casting. Some of those things that crop up, and we know it now, a lot of us do, that have dug in and tried to figure out what the problem is, because we get the quote unquote porosity defects that customers say, hey, this casting has porosity in it. And generally, when you just go pull out your small handheld microscope and you go look at it at 100x magnification, it's like, well, that porosity is actually shrink. We have a shrink issue, and we need to deal with that. And a lot of those things that we run into defects, because defects and mitigating those defects in metal casting is the problem solving that we do day to day to day. It typically has to do with shrink, in my opinion. It seems to be that the shrink manifests itself is a big problem, but biofilms obviously contribute to all of that.
I think you wouldn't see much of your shrink if you didn't have biofilms, because the metal can't pull
Right.
itself apart, but it comes apart very easily if there's a biofilm there, and then it starts to grow a shrinkage cavity for you. Because, and again, that was one of my early findings right back to my PhD days with casting these little turbine blades, and because I was pouring them in investment molds, which we could make very hot, you had plenty of temperature in your metal such that it stayed softer for longer. It didn't get cold quickly at all. So it had time, and it had low strength to be able to collapse under internal shrinkage problems if there were not biofilms there. If there were biofilms, it would open up porosity. But if there were no biofilms, it couldn't open up. And so the outside collapsed inwards. And that was an effect I used a lot in the Cosworth casting process, because our metal was reasonably clean of biofilms, not completely so, but not too bad. And so isolated bosses on castings, I never bothered about feeding them. They always self-fed by collapsing ever so slightly you couldn't measure or detect. But it was very helpful because our castings were very complex, and getting feeding to some of these complicated chunks would have been a nightmare. But I didn't have to worry about it. They got themselves solid.
Okay. Interesting. So, whenever is there something that we can do as foundrymen, metal casters, that we can help mitigate some of the biofilms whenever we need to transfer or we need to move metal from a furnace, a traditional furnace, induction furnace, it could be a gas furnace for aluminum, to the pouring ladle, because a lot of times we have to use a lip pour ladle. So is there something that we can do with transferring from there to the pouring ladle so that we don't introduce more biofilms? I mean, we have to be very careful about the gating systems and how we engineer those so we don't introduce more turbulence and create more biofilms as we fill the mold.
Well, you're putting your finger right on a major issue for the whole foundry industry, and that is the transfer from the melting furnace to other transfer systems like ladles, etc. And this was the very reason why I set up Cosworth process in the first place. I said, right, we're going to make castings without pouring at all. And frankly, it wasn't difficult to do, and it was immensely successful. I mean, it saved the Cosworth company. The fact that you needed engines which would get you over the finishing line was something you had to have. And suddenly the foundry gave them that power. It was an immense sales benefit. They could promote their castings with the full guarantee that they would get it over the finishing line. So this whole business of pouring, when I did the Hoyt lecture for the AFS, the American Foundry Society, I'm just trying to remember my title now of my lecture. Oh, that's right. It was it Stop Pouring start casting.
Art casting.
Yeah.
Yeah, I remember that.
Yeah.
I have the white paper that was written for that.
Yeah.
Yeah, it was excellent.
Yeah. Well, it was just a new way of looking at how to make castings, and I've never changed from that. And this big project I have now in the UK is a counter-gravity project in which we never pour the metal. So the concept continues in my own mind because of the genuine problems that pouring gives you. And I mean, there you are. You've just described it. It makes your life hell. And if you don't have to pour, then that's the technology to go. And it's that does mean big changes in the foundry, but ultimately it solves a lot of problems. So yeah,
Yes.
it's that's a hard decision to take, to move from gravity pouring to totally to counter gravity and to eliminate pouring from the foundry. But if you were making a big repetition foundry nowadays, I wouldn't think of doing it any other way.
Sure. Yeah, and I remember when that lecture was put out because it was shortly after I had, or the same year, 2012, when I went to move from Oklahoma to Houston, Texas, to do copper-based and aluminum alloys. And when I got there, there was, I mean, you need to pour that metal, and nickel aluminum bronze as an example, C955. I mean, it has a high propensity for
Oh
oxidation.
yeah.
Shrinkage is outrageous. Not as bad as shrinkage in C954 aluminum bronze. It's worse, but the oxidation and the scabby looking crap that floats on the metal
Yeah.
when you pour that in a turbulent manner, it's insane how nasty that alloy is. And again, rule number 2, to eliminate turbulence, of your top 10 rules. Start with good melt stock. We always use certified ingot, and we still do today here at KN Manufacturing in Lufkin. So I mean, all those things. I remember reading that, stop pouring, start casting. I was like, what is he talking about? I read this, and it made a lot of sense. The problem that we run into as metal casters is because of the traditional way that we've always poured castings has been melt, transfer to a pouring ladle, whether it be a teapot ladle or lip pour ladle, and we go pour, or even a bottom pour ladle for a lot of different applications. But people need to see the practicality of how that works. A lot of people a picture, it says a thousand words. And if they can see something like that being done, it makes all the difference in the world. We can talk about it, but until we start being doers and doing those type of things and showing other people and teaching them and coach and mentor them along the way, the light bulb is not going to go off. And that's the fun part that we get to do during the podcast. It means there's going to be some people that will be like, hey, Professor John Campbell, they're going to go look for the stop pouring and start casting article for the Hoyt lecture that you did in 2012. And matter of fact, we'll put a link to that on the podcast so that people can get it easily and they can get some of that information, and the link to also to your mini casting handbook in the 3rd edition and that sort of thing. We gave one away recently. We gave it to Clark Easterling at Windy Hill Foundry actually a few weeks ago, which was fun. So yeah, it's one of those things where the more that we do and the more we can continue to educate and talk to people about these things to eliminate these biofilm. And I think, do they still call it biofilm theory?
Yeah, biofilm technology.
It's not really a theory. I mean, it's
No,
proven.
that's right. I call it biofilm technology. It's because it's a wide subject now. But
Sure.
with your Hastelloy type, nasty things you've got to cast, at least all the oxides are much lighter than your metal. The metal is very dense, and so the great thing there is that it floats to the top. Your defects tend to float, which means that if you could access the metal in the bottom of your container, that's your best metal. And so the whole business of contact pouring using bottom pour ladles has been very, very successful. And wherever I've been able to introduce it, where there have been bottom pour ladles, but they haven't been using contact pouring, in fact, they deliberately don't contact. You see the stream pouring, and the man watches the stream pouring. He believes he has to control it. But I say, look, to hell with that. You put it flat down on the mold and engineer yourself an airtight joint. And I've seen lots of people engineering this joint in all sorts of ways to stop the air getting in. And so there's no one solution, but it's the contact that matters. And so contact pouring has been a fantastic benefit in the foundries where I've introduced it. It's been the first thing I do as I walk through the door. With most big foundries making big castings, if you're making small castings, you can't do it. It's too fiddly and all the rest of it. But for tonnage products, it works like a miracle.
Yeah. What is a common thing that is used for that contact pouring, for that gasket seal off whenever they make contact with the mold?
Well, the ladle normally prevents you making contact because the ladle's got feet which get in the way. So you can't actually lower it onto your mold. So you need something like either a nozzle extension from your ladle or a sprue extension from the mold, because they've got to meet somehow. And in general, the sprue extension's the easy one to do, even though you can get slightly longer nozzles, which is helpful. And then you just need a soft gasket, a ceramic paper type gasket.
Rope or something?
I wouldn't use rope, but I'd cut gaskets with a pair of scissors and put them there.
Okay, yeah, like a ceramic rope that would go on like a seal of an oven or something like that?
Well, okay. If you could keep it on, whereas a cut paper sits in place and stays in place very easily, and that's a good
Cut paper, okay.
Yeah. So ceramic paper, yeah. The ceramic fiber.
Ceramic paper, okay.
Yeah.
Okay. Yeah, and so these silly questions like that, that's the practicality stuff that actually makes the light bulb go on faster for most people. And that's the reason why I ask, because we can talk about stuff all day long, but until we actually teach and show people what to do, it's a moot point. And what we run into is a lot of times people keep that information so close to their chest because they want a competitive edge. But it doesn't really help humankind. It doesn't help the metal casters down the street or anything like that. So it's definitely one of those things that is near and dear to my heart, because without us teaching one another and helping each other, I mean, it's for naught. So,
yeah.
Matter of fact, we had a podcast recently with Jared with NIFS, Jared Weaver, and he was talking about they got a technical committee that they're putting together for nickel, aluminum, bronze, and aluminum bronze, and they're actually going to be networking with some people from the UK and Australia and things of that nature. They really need to talk to you, is what they need to talk to. Professor Campbell needs to be on that at least advisory board.
Well, he said that would be surprised at who was going to be on there, so I just assumed it would be Professor Campbell. That he had already contacted
I hope so.
him.
He's going to be hush hush about it, I think.
Oh.
I've always had the impression, Professor Campbell, that your message tends to be a little polarizing. People that I've talked to, either they accept it and they live by it, or they just reject it. And I wondered, why is that? Why are you such a controversial figure?
Yeah, I wish I knew, and I wish I wasn't, because no, there are some people who are good at winning friends, and maybe I'm just good at winning enemies. I mean, it's not something I do intentionally, and I wish it didn't happen. But yeah, I think I have more enemies than friends. And, I,
It's
I think
I
there are
always find it just
people.
remarkable.
Yeah.
Nate, is it because of the old school way of doing things and people
Well,
just won't let
I
go?
wonder whether
Well,
it's them or me. I think there's a good bit of it in that's me as the problem.
Really? Do you think
And
it's you?
I don't know what it is, but I suspect it is, and I don't know how to change it. So I think it's some of it is them, and some of it is me, and I don't know what it is really.
Well,
Wow.
I suspect that some of it is confusion, to be quite frank, because it's not your personality, Professor Campbell, at all. I mean, you are a soft-spoken individual. I've never seen you get excited or pissed off or yell or scream or anything of that nature that would drive people away. So I suspect it has something to do with the confusion and the old school mindset that buy film, which is not a theory in my opinion. It
Mm,
lives and breathes in our day to day
mm,
lives when we
mm,
pour these Newtonium alloys. The
mm,
problem that you run into is that I think that's a lot of the old school guys, which are I mean they're leaving the industry because they're getting up in age and they're either closing their foundries or they're selling their foundries. So there's a lot of new people that are coming through that are using a lot of the knowledge as more of us talk about it, and it requires more networking on our part. It requires us to be humble and allow us to educate other people along the way, as guys like
mhm,
myself learn it. Do I implement 100% of Professor Campbell's 10 rules? I try to, but
mm,
in the foundry business, and especially if you have existing business, guess what we have to do? We have to be able to make payroll, we have to be able to cash flow, and we have to get castings out the door that meet the needs of the customers for form,
mm,
fit, and function. If we don't do that, we're not going to have a foundry to actually run. And I remember you sent me an email here at the beginning of the year, saying, "Hey, you and your wife Kelly, you really picked a difficult way of making a living in the foundry industry, and it's not for the faint of heart at all." It really truly takes a lot of grit, tenacity, and determination to not quit and to show up every day and trying to be better. And in that process of doing that, that's how I came across your literature and your books and that sort of thing, because I wanted to be a better founderman, because the answers that I was getting from the old school guys, guess what? They were non-answer answers. It was a bunch of pixie dust and voodoo that they could not explain at all. Well, it was like it's math and science, and there has to be some sort of an explanation for it. And I thank the good Lord that I came across your information and read about biofilms. And matter of fact, Jack Rice, which was the owner of Texaloy Foundry in over by San Antonio, he's the one that had your book, the big thick book, the
mm.
one that's on the shelf right there.
Oh yeah,
It's the metal casting Bible as far as I'm concerned. Yeah,
yes,
right there. I keep
oh
it I
yes,
keep it
lovely.
very handy,
Mhm,
and I do that on purpose. The little books that you produce, the metal casting handbooks, I give those away, man. I'll buy those 10 at a time, and I'll give those rascals away,
Where
and I do it and
where
it's a quick read.
where do you buy them? How do you buy
I get
them?
them on Amazon,
Oh,
Amazon a
okay.
lot of times, and a lot of
Mm,
times
okay.
I can get them from AFS bookstore as well.
Can you?
Yeah, the last
Oh,
bundle of books I bought them at one of their events. They had some on the shelf.
I'm really happy to hear you say that. Um, I I worried about the AFS bookstore because there was some time ago that AFS was appeared to be promoting this book on how to make castings without using any formulae or anything like that. And so I thought, oh,
Mm,
well, if there's a way of making castings without formulae, I need to know. So I sent off for the book.
right.
It was, I think, if I remember rightly, it was about 85 pages. And as I went through the book, every page was wrong. Every
Ah,
page. Okay. So I got to the end and thought, wow, if the AFS is promoting this, this is extremely serious for the industry as a whole. So maybe the situation's a bit mixed at AFS, and if they've got some of my books and some of these 85-page efforts, maybe some good will come out of it eventually. No.
well, I think that we have to continue to fight the good fight when it comes to good processes. I went to I went to Chicago, Schaumburg, or whatever, however you say it, in by Chicago, for AFS gating and risering school. I still have the book sitting on my bookshelf over here that I reference from time to time. Ian Kay was the one that taught that class. Very, very good guy,
Oh, Ian, he was a
and
nice chap. I liked him. Yeah.
he he was outstanding.
Mm.
And one of the things that he drilled into our heads, and this was crap, 28 years ago,
Mm.
is pour as fast as you can with the least amount of turbulence. I don't know. I don't. If he said that one time, he said that 100 times during that week, and it was a completely true. And it goes hand in hand with a lot of the things for the casting practices for the top, the 10 rules. Avoid turbulence and entrainment. I mean, he was saying the same thing you were saying,
Mhm.
just in a different way.
Yeah.
But
Okay.
it didn't break down all top 10 rules per se, because they were trying to cram a lot of stuff into 1 week class. You can only
Hmm.
do so much.
Hmm.
Very difficult to pull that off, and he had a difficult job to do.
So you just got
Is
back from an AFS event, right, Nate?
Yeah, so I just got home last night, like at 11 o'clock, from the AFS Government Affairs fly-in there in Washington D.C., which was extremely good. As we had the podcast when we had with Chris Greenfield. Of course, Chris Greenfield with Non-Ferrous Founder Society. He's the chair of the Government Affairs committee, and Chris is a great guy to be on the side of metal casters. And of course, I bumped into him there at the conference as well, or the meeting. The cool thing is, most Foundry guys, when they deal with government affairs and things of that nature, they just leave it to the trade organizations or the few people that show up. And it was actually a good turnout. I think there was probably 70 people there, or so, which were going to the Hill, on the House and the Senate side, which was extremely good. And Chris made a point. If you're not at the table, you're on the menu, or you could be on the menu, and that is entirely true, because when we go to government affairs and you talk to those individuals, you would be surprised, because a lot of the staffers that you meet with, which are the individuals that I like to talk to anyway, because honestly, the chief of staff and the legislative directors and the assistants, those are the guys that are actually doing the work, right? The politician themselves is one individual. They can't do it by themselves. Just same thing as in the Foundry, right? I can't run a Foundry 100% by myself without a team, and it's no different there. So it's always good to be able to educate those younger people that are in those positions, because a lot of times you ask them, "Do you know what metal casting is?" And they're like, "I have no idea what you're talking about." So then you have to, it's our job to be able to, to provide some sort of a knowledge, and do it in a way that is fun and
Mm.
articulate, and so they understand what we do and how important it is for every other industrial sector that's out there.
Yeah.
Without castings,
Mm.
these other sectors just don't exist. And I don't care if it's plastic or anything else. Without those injection molding machines that require castings and other things, forgings and extrusions, they're not going to produce a piece of plastic. They're not going to be able to they're not going to be able to make anything that looks like that, without some sort of a casting in the process of doing that. So it's a lot of fun to be able to educate those guys. So yeah, the AFS is doing some good things. But again, NIFS, Non-Ferrous Founder Society, they're doing some tremendous things with the committees that they've got. And you'd be surprised. Texas Metal Casting Association, they had Stan Bass is the president of that. Met him, and they're doing great things. More smaller regional things for metal casters, which is very encouraging, which is a lot of fun.
Okay. Well, it's good to hear what you say, Nate. What I find occasionally, from my point of view, is that people say, "Oh, yes, I've got your book," and they produce my book, which I wrote in 1990 or something. And, and I can't very well say to them, "Oh, we'll put that in the bin," because it's not totally wrong, but technology moves on, and even with the latest books, the handbooks, they're now the small one, the mini handbook, is on edition number 3, and edition number 3 is a significantly different from the first edition, but you can see this thread that carries through them all, but you do need the most recent technology, and this is a problem I find. People don't know that there are new editions coming along, and they've still got the old editions, and somehow they're missing out on the latest technology. So yes, I'm always pressing people to get the latest edition. I'm working on the 3rd edition of my big book at the moment, and that's
Fun.
not quite in a catastrophe situation, but I'm really struggling with it at the moment. And what's happened is that the copyright rules come along, which suddenly authors have to buckle down to getting right. And this makes life very, very hard for a technical writer. And as I say, I'm struggling with the 3rd edition of my big complete book at the moment. And it's a pity
Yeah, I was
because,
trying to think. I had the first edition, and I think the one that I have is the 2nd edition now.
yeah, the 2nd
And
edition is at the moment the best. 3rd edition was due to come out soon, but it's going to be delayed.
the funny thing, the funny thing is, I have the mini casting handbook. I have the 1st edition, the
Yeah,
2nd edition,
yeah,
and the 3rd edition, and it's fun to be able to see to go back and look at those and see how they've changed.
yeah.
Because when you look at the 3rd edition, I mean, it talks of, and obviously that has probably changed as well.
Mm,
It's always good to know, some of the when it talks about the vortex, the gate, and things of that nature. It's always interesting to see how that works. The trident gate, for example, with the bubble
mm,
traps
mm,
and all that sort of stuff is a lot of fun.
mm,
We implement a lot of those type of technologies in a lot of our, especially with 3D printed mold packages. We can get so creative with the mold packages.
mm,
We can get really, really. It takes the complicated parts out that aren't conducive to the traditional two-part mold, the cope and the drag
yeah,
situation. Sometimes we'll have a 4-piece mold.
mm,
Sometimes we've had a 5-piece mold, depending on how intricate the part needs to be with a 3D printed mold package. But the
mm,
cool thing is we get to do that. We found a lot of times with the traditional surge traps or traps in general at the end of the gating system, we found that when the metal hits the end of that gating system and then it reverberates back and creates waves coming back, what it does to put the damage the metal even further. I've actually we've engineered some jobs that using real thin and wider sprues and runners so that we can meet that vertical to horizontal transition and taking the splash well out of it, which is a cauldron for bifilms
mhm,
and all the defects that get created by damaging the metal. People don't think about that because the old school mindset is the fact that you pour the metal in there, it's all the same, it's no big deal. But what the problem is, when they can't see into the mold when it's
mm,
filling and when it's priming, the gating system is priming, they don't realize how much damage that they are actually doing because of bubbles and all the other things that come along with being able to prime the gating system.
mm. Yeah. Well, I think simulation has helped enormously, and it's done the industry a great service, and that's altogether positive. I suppose what isn't positive is the sense that once people have looked for shrinkage and got rid of shrinkage, they then don't worry about the damage they've done, with the turbulence itself, and generating oxides and biofilms. But I have to say, my new running systems now, which are described in the latest mini book, which you've got, I enjoy using them, and we get the most beautiful castings out these days, and we've made some really lovely pump castings for aerospace, and the things turn out, frankly, they turn out excellent first time, which is the thing we're always aiming for. Well, it's just happening now, and I'm as I say, I find it's a pleasure to use my latest systems. I think I've finally arrived. The interesting thing to say about it is that the just straight pouring now, gravity pouring of castings has now become so good that if I'd invented all that first, I would never have bothered with counter-gravity like Cosworth process or anything. That would never have got invented if we'd had the good gravity pouring systems. However, having said that, I'm now working on with a company. We're building quite a substantial machine to take secondary aluminum, recycled aluminum, process it, get rid of the bifilms, and then cast it uphill using a pump to put it into a mold from below under control. And what's more, we have a way of getting it off the casting table. Immediately, the second after we fill, we can move it. And that means that you can make, say, a casting weighing several kilograms in, say, 20 seconds or something like that. Then in a very few seconds, maximum 3 or 4 seconds, we can move it out of the way, move another mold on, fill it again, move it away. And this turns out to be, I think, probably the fastest casting process in the world, but producing, frankly, excellent castings. And what's more, it's easy. And what's more, it doesn't cost a lot. So it has all these sort of dramatic and important features, which are all coming together with the good technology. And that's a nice message to get across if we can. So yeah, I'm hopeful about the casting industry. I think it'll get there. It's just hard work at the moment.
So you had mentioned several minutes ago, I'm pretty sure you said something about the industry not being able to charge enough, maybe not to be able to pay enough. And we had a conversation just the other day with an individual who was talking about, and we were speaking of the dreaded tariffs, and he was saying, one of the problems that the American foundries have anyway, and this may be true of other places, like the UK or something, is you've got countries that are largely unregulated, producing mass numbers of castings very cheaply.
Mm-hmm.
And I'm curious, how do the more regulated countries, America, the UK, how do we deal with getting prices up when we're competing with countries that can just throw metal down a hole and get some semblance of a casting and sell it?
Yeah. Well, I don't think there's a straightforward answer apart from the fact that we're using a better technology, and because it's controlled, we should be able to control the price better. But we are up against the sheer cost of energy and the cost of the metal. there are certain things we can't change the cost of. And, so, yeah, it's going to be a challenge. And some of them we're going to win and some we won't, I think.
Is it is part of the answer just the type of casting that we're doing? I mean, I would assume something like casting an impeller is far more technical and maybe harder to do than casting a frying pan, or something like that, right? Is it do the industries kind of diverge as to what they're making?
Well, I shall never forget going around a propeller foundry and seeing them coring up these things. And frankly, I couldn't understand how the thing was cored up. I mean, it was, there have been old chaps working at that, and they knew far more about their subject of making their castings than I could understand. I thought that was amusing. But it actually reminded me when I was first qualified with my PhD, and I went into a foundry, and as I entered, there was a chap sitting on the floor doing some floor molding. And I stopped dead, and I thought, that chap knows more about making castings than I do. And that was where I started with the industry. It was a big shock, and I had to eat a lot of humble pie and learn the job, bit by bit. I think I'm there now, but it was not a quick job and not easy.
So did you start working foundries after your degrees? Or is it?
I did my, well, I went up to university to study physics. Having got there, I then found there was a subject called metallurgy, which I thought, that's far more my kind of subject. So I moved, having become fairly well trained as a physicist, I moved sideways into metallurgy. Having done that, I was very much taken up, because those were the days when the electron microscope had only just been invented. And the other thing which was just invented was the microanalyzer, which was such an exciting tool to use to look into inclusions and analyze the individual components of the inclusions. And I thought, this is the kind of thing I want to develop and work on, which is very much sort of solid state, electron optics, this sort of thing. So I went back to university to try to get a PhD course in that. But at that time I had no money, and I was a typical student, and I had to accept the only PhD position which was funded. And it was funded to look at simulated cast turbine blades. And I thought, this is total disaster. I can't get my electron beams to focus on liquid metals. And, this is a subject which couldn't be a worse choice for me. Anyway, having got into the subject, I absolutely loved it, and so I was making castings for my PhD. And what was interesting, these were simulated cast turbine blades in cobalt alloys and nickel base alloys, and the problem was to cast them in such a way to get them sound. And so right from the earliest days, I was into casting defects and how to get rid of casting defects. And those were the days when the turbine engines for aircraft would not use cast blades in the turbines. They were all forged. But I managed to get some sound cast blades by casting in those early days. And I like to think that that might have influenced the industry. So it was Rolls-Royce that was supporting me, or at least partially supporting me at the time. There were other aerospace companies in those days before they all disappeared. So it was a conglomerate that was putting the money into my research. But it wasn't long after that the first cast blades and cast buckets came into turbines, and frankly, the world hasn't looked back.
I have another question. Biofilm theory.
Oh, yeah.
And you mentioned the electron microscope and things.
Mm.
So, when did you see your first biofilm? Was it a case of there's something in that metal, what is it? Let's figure out what it is. Or was it we figured out we had a theory on biofilm and there's one. I see it now. What was your first experience with that?
Well, now, this isn't an easy question for me to answer because I don't know when it was, okay? And I have real problems to remember how the concept evolved because I think it first started when I set up the Cosworth process and I ran the Cosworth Foundry, and we had an electromagnetic pump in the liquid aluminum, and it was connected to a large steel casting table, a 2-inch thick steel plate. It had this little hole in the middle through which the metal came up. And what was fascinating was that we could control the pump to bring the metal up and hold it there level. But if then we suddenly pressed the button, the metal would jump the heights that we said, we programmed it to jump. And then you would see something. You saw the metal came up, became like a little mushroom, and started to fall back on itself. And I thought, that's interesting. And I think it was from seeing that happen on our casting table in the Cosworth Foundry, that's where the idea first came to me, that the metal can fold back on itself. And I thought, yeah, maybe that's the secret of how the defect forms, because the oxide layer is coming against another oxide layer, dry side to dry side. And the concept evolved from that. So that's as best I can give you an answer.
Like so many things, if you have someone who's willing to look at something with a curious eye and say, why is it doing that? That seems, there seems like there's something going on there. And, unfortunately, so often people just, it always says that, right? They don't think paying attention to it. But do you remember actually seeing a biofilm in a casting, like an X-ray or whatever it was? Do you remember your first time seeing one? And just kind of having that moment of, there it is.
No, but let me give you another instance whereby the whole concept came together. And that is when we set up, when I set up the Cosworth Foundry, we had this big holding furnace with a ton of metal in it that sat there for 360 days a year. People thought we were mad in those days, because they melted, once or twice a week, and working from pots that had cooled down and absorbed moisture, and then they're in hydrogen problems again. So we were never in hydrogen problems with our melt. Actually, I tell a lie. There was one event when we added strontium, but let's not worry about that for a moment. So we had the ton of metal, it just sat there in the furnace, and what I wanted it to do was to sediment any things in suspension, because what we didn't have in those days was filters. People had only just invented filters for liquid metals, and they weren't generally available. So without filters, I thought, how else are we going to get all the debris out of the metal? So I got the big furnace, left it there, allowed it to sediment. And so we got actually remarkably good castings, wonderful fatigue results. And so we knew we were doing something right. We knew there was something in the metal that was sedimenting. And then there was one day when we decided to add some grain refiner, and we got the castings. They were beautifully grain refined, but they were all scrap. And because what you could see was that every grain boundary, every grain triple point between the three boundaries coming together, there was a hole. I mean, the castings were so porous, you couldn't believe it. And all the theories said if you get finer grains, you get better feeding, so therefore you get better soundness. But we'd just proven the opposite and made totally unsaleable castings. A whole day's production's worth. You don't forget these events in a hurry.
Yeah.
And my quality manager, Michael Flynn, an Irishman, he said, you know what we've done? When we added the grain refiner, we stirred the melt to make sure it was properly mixed. And then we made our castings. Yes. And so the whole business of connecting our defects with something that was in suspension in the melt, you see, there was, little by little, we kept stumbling on these situations. So we grew to have an appreciation of there was something there which we had to keep out. And I can't remember. Oh, yes. I got a job to go and assist a foundry casting aluminium bronze. And they had a furnace with must have been a ton or more of aluminium bronze in it. Probably maybe, coming to think about it, it was at least 3 tons. And they had a ladle, but they had no ladle heater. So they would heat their ladle by tipping up the furnace, pouring the aluminium bronze into the ladle, tipping the ladle, pouring it back into the furnace, tipping it. They'd do this about 3 or 4 times, and then they'd go and cast it. Well, what you saw when the ladle tilted to make the first castings, it wasn't liquid which came over the lip of the ladle and started to pour. It looked like a slurry of cement, almost. It was granular, practically, and poured. Anyway, so that was interesting. But then I saw the X-rays, and whatever it was that was in the casting had floated to the top of all their castings during its solidification. And you could see on the X-rays that these were very thin films, but some of them were the size of your hand. And that there were hundreds of these all floating at the top of the casting. And so again, there was another example of a major defect arriving in the casting because of the oxide. Clearly, it was the oxide film that was a problem. And so our knowledge of the problems of oxide films built up over the years right from about 1990 right through. By about the year 2000, we got a pretty good idea of what we were dealing with, and that was about the time I first thought of, okay, we better give them a name. I better call them bifilms, and because they're a very specific defect with very specific properties, and we just need a name for them. And since then, there's been quite a number of researchers around the world. People have latched on, researchers have latched on, and done quite a lot of research on it now. And I think we're starting to understand bifilms quite well. And what's been amazing about the concept of the bifilm, it's been enormously more productive than I expected in the first place. I thought it was a rather humble sort of thing, which it is, but it gets into everything. And it's in virtually all of our engineering metals. And so the very steel work which, our factories are built from, and our motor cars are made from, all of these are crammed with bifilms. Millions and millions of bifilms in every component you can look at. And what's more, the bifilms are in control of the properties. And this is something the metallurgical profession doesn't yet know. I'm trying to spread the message, but because I found unlearning my metallurgy and relearning it with bifilm content was not an easy thing to do. So I don't expect other people to find it easy. And they like their metallurgy as it is. It's simple and uncomplicated, even if it's wrong, which it is. But you see, you can't blame them for taking offence when I say it's wrong. I try not to be so blunt, frankly, but there it is.
Well, yeah, it just seems like, you say it's hard. I guess it's hard in the respect that as you just said, it's hard to respect that you have to let go of what you've always done and start thinking about things in a different way.
Mm.
It's funny to hear you say that, because for me, I started off knowing nothing, and I was introduced to this almost immediately. And so I didn't have to unlearn. I didn't have to let go of anything. I just accepted what was happening. In my little foundry in the garage, it just made perfect sense to me. But I hadn't been doing it for 20 years, and I didn't have all that other experience to have to get rid of.
Yeah. Well, I think foundrymen have a better chance of switching into it, better than anybody, better than metallurgists. The metallurgist has a big problem switching into bifilms because he can't see them in his metals. And even the electron microscope struggles because they're nanometer thick. They're only some of them are only a few molecules thick. However, that contrasts with those that are microns thick and thousands of times thicker, and they're easy to see. But as I say, most bifilms, the huge majority, are pretty well invisible, which means that the metallurgists have great problems to believe they're there. And the other reason they have a problem to believe they're there is that although they're in the form of cracks because of the lack of bonding between the two films, the cracks are closed cracks. And when it's only a few nanometers thick and it's closed, you've got a challenge to see it. I mean, it's really, really difficult to see. However, you put on a load to plastically open and to fracture the metal, and these things open beautifully. And so all the things that metallurgists remark about, like cracks opening ahead of the mains propagating crack, these are all things you would expect because of the population of cracks which exists in the metals as pre-cracked metals. There are a few of our metals that don't contain bifilms, and they're really interesting and different. And but for instance, pure copper is one. It's very often it's melted under charcoal, and that means, and the copper oxide is reduced by the charcoal back to copper. So copper can be very, very clean, and why it's one of the reasons it has its good conductivity, of course. But there are it's steels as well, like the boron steels, where the oxide is now a liquid borate, and now you fold that over, and it's just liquid to liquid, and it just balls up under surface tension into little spheres, and it floats out. There's my clock, which dates from the late 1600s. And every time I wind up I have to wind it up every day, pulling the weights back up on the chains. And
Yeah.
I always wash my hands afterwards. I think all the leprosy and the bubonic plague that is on these chains, I owe it to myself to wash my hands afterwards. So yeah, but it's a very good clock. It keeps marvelous time. That's when I don't forget to wind it up.
Part of your fitness regime, is that what?
Well,
winding the
absolutely.
clock?
I need the exercise. Yes.
I have another question. I've got 1,000 questions, but so when we're looking at well, two things, I guess. First thing you said, metallurgists have trouble seeing it.
Hmm.
I'll take it to the philosophical. Is that because they don't believe and don't want to see them, or is that because they're just hard? You said they could see them in cracks, but is there an aspect of this? It's just like, I don't want to believe these things exist.
Sometimes there is an aspect of refusing to believe. Yes, that's right. And in fact, I've had very senior scientists say to me, I can't see it, therefore it almost certainly doesn't exist. Well, you think, hang on a minute, we can't see atoms normally, and
Right.
can't see Disney. For years, there was the professor of metallurgy in Sheffield, Arthur Quarrel. He was a very distinguished professor of metallurgy. This is some decades ago now, and he refused to believe in dislocations because he couldn't see them. And these are very curious attitudes to take, to not believe in it just because you can't see it, when lots of things in life are like that.
Lots of things in life are like that.
Yeah,
Yes,
For
they
sure.
are.
yeah,
So
yeah.
before we get off this thing, one other question. So I've often had this in the back of my mind. Do biofilms exist, and do they continue to exist from the ingots that we use? I buy an ingot.
Mm.
Is it does it because of the way the ingot was poured, are biofilms in that, and then do those biofilms sort of propagate themselves into my casting?
The quick answer is yes. Yeah, I mean, the ingots you buy are poured. Some ingot casting machines pour better than others, but there are some which pour really quite badly, and you'll have a good population of biofilm cracks all the way through. And what's more, they'll survive remelting, and they will survive pouring, and they will add to all the others you cast, together with the pouring and your running system. So you have the chance with a metal like aluminum of, at every stage of its processing, its biofilm content continues to go up, which is what makes the secondary metals quite difficult to deal with. They are crammed with defects. And people are just looking at the chemistry and saying, oh, well, there's a lot of copper. But, that's secondary, in my view, to the
But,
oxide problem.
well, you keep saying things that keep driving me more questions. What about recycled aluminum? Everybody I keep hearing, oh, we should be recycling aluminum, especially here in the States, because it's takes far less energy to recycle aluminum than it does to actually create
Yes,
or,
yes,
or smelt
absolutely.
aluminum, right?
Mm.
What about, recycled aluminum just a mess in terms of biofilms?
Well, I think people are doing different things, very often without knowing it, to reduce the biofilm problems. For instance, they use filters. And filters are, again, depending on how you use the filter, it can be fairly good or not so good to reduce the biofilm content. But the other thing which has a profound effect is the process of grain refinement, of adding something like titanium and boron, very often in a rod form, and putting that into the melt. And magically, the bifilms will mostly disappear at that moment. And that's because the titanium compounds precipitate on the bifilms, makes them heavy, and they sediment. Now, the last thing you should do is stir the melt before you pour it, because then they all go back into suspension again for those few seconds while you pour. But so you then get a beautifully grain refined casting, but it will be awful. Its properties will be dreadful. Whereas, as I say, if you simply add the grain refiner, let the biofilm sediment, you stir in the grain refiner, making sure it's homogeneous, and then don't touch it. Go away and have a cup of tea, come back 15 minutes later, and then pour your metal, and your properties will be quite different.
Mm. Is there a time limit from the time that you add your Tibor
It's
or your boron so that
in general, what I see around the industry is this process takes just a few minutes. There are plenty of metallurgical processes that take hours, but this is one that's pretty quick, and it's really very effective. And then, of course, because your casting is then grain refined, and people measure the grain size, and they say, "Oh, yes, its better properties are because of the smaller grains." that's a secondary effect. Now, again, metallurgists don't wish to know that. Your good properties are the fact that now your casting isn't full of cracks, isn't full of bifolds anymore. And that has a massive effect upon the properties. Whereas the grain refinement is a positive effect, but it's secondary to the biofilms. And that's a difficult message to get across to metallurgists.
Right. Yeah, for sure. Is so when it comes to Tibor and strontium additions, which are used significantly in the metal casting industries for aluminum, a lot of times what I see happening on the floor is they've got for smaller aluminum castings, they've got a dip out furnace, so they'll have a hand ladle. They'll throw the titanium and strontium, the Tibor and strontium sticks. They look like the size of a pencil, whatever size they need to have, so that it meets whatever they're dipping out of these furnaces with. They'll throw them in there. They'll dip out, and they immediately go walk towards the molds and go pour them, and then back and forth until they get the mold line poured, and then obviously they'll allow the melt more metal and bring it back up. But they're typically never utilizing 100% of the melt. They're leaving a heel in the furnace, and then continuing to rinse and repeat as more molds come through the mold line. Very efficient way of doing it. But the amount of Tibor and strontium that is being used, I mean, there is no lag between the time that they dip it and the time they go pour, other than the time it takes for them to walk.
They're missing out. They're missing out on a valuable effect, which just needs just a few minutes. Yeah. But if that's in a
so is it better for them to
I wouldn't do it in the hand ladle, because you don't have the time, as you say. The hand ladle's cooling too quickly, which is why I would do it in the furnace, because the furnace has no problem to hang about with temperature and give you the time. And one dose, one stirring in, one wait for them to sediment, it should work pretty well.
And then at that point, you could take a sample from that, take it to the lab. You could check the microstructure, and you can see what it is, what they're actually going to dip out and go pour. So that to me makes a lot of sense. Yeah. One of the things that we run into when we're casting aluminum alloys, especially A356, T6, it's probably the vast majority. It's the most common aluminum alloy that is cast in the world. I'm guessing. But it's got a very it's almost got an embarrassing low elongation of 3% as a standard, which is to me is just like, well, this is just terrible. This is not, even ductile iron, for example, 65, 45, 12, you got a minimum elongation of 12%, or 80, 5506, a 6% elongation. For those people that are listening to the podcast, I mean, I know I have some family and stuff that they like listening to stuff. The elongation is how much the metal will stretch before it actually breaks. And with 6% elongation, when you think about that for an 80, 5506 ductile iron, well, when you take a step back to the aluminum, the A356 is a 3%. You can barely move it, and that stuff snaps, and it's just like, this is almost, it's amazing that we can produce anything with any confidence to be able to use it as a metal. But there are much better elongations that far exceed by 10x or more that are being done today. Is that a true statement?
Yes. In fact, if you, the famous example is our friend Bob Puhacker, and he's getting 20% elongation in his 356 alloy. But he's taking unusual steps again to sediment bifilms, and for instance, he's not adding you need to contact Bob, really, to get the details.
I understand.
Okay? But he's taking a lot of
I get it. Yeah,
and he's got all the success, But
Right.
I mean, I think the last
And
time,
as you
Maybe you
should.
can put in a good word with us with Bob's so he'll return our
well,
calls.
when he first contacted me, when he first set all this up and he got his first 20%, I think I wrote back to say, why only 20%? Why didn't you get 100? You know, because
Oh yeah, I love it.
well, I really think that if we really get rid of the very last biofilm, we should get 100%, and metals should neck down to a point when they come apart. And you know, what was interesting with Bob's work with good running systems, which predate his aluminum foundry, was when he was working in a steel foundry, and he one day got 75% in a steel, which the customer wouldn't believe. But so the good running systems are reducing those, the population of biofilms is the way to go. And the biofilms are in control of the toughness. For instance, let me tell you about the steels. There's a lovely foundry in Sheffield that I'm very friendly with, and lovely people there. And they're now using some of my methods, but what they've moved from a situation where they used to cast their super duplex stainlesses, but many of their castings failed because they couldn't meet the 40 joules Sharpie V-notch. Is it a Sharpie V-notch? It's certainly a Sharpie anyway. And but anyway, having plugged in a good running systems and keeping air out of the system, they now never get below 100, and sometimes they're approaching the 400. So they've moved upwards in toughness by nearly a factor of 10. I mean, these are not trivial benefits. And I mean, when you see people researching toughness in steels and they get maybe 5% increase or sometimes 10% increase, whereas my Sheffield foundry's got nearly a factor of 10. I mean, it's just mind-blowingly different. And again, the biofilms are in control. It's not the metallurgy that's generally in control. Again, metallurgists don't wish to know.
Yeah, and that's the amazing thing, because stop and think about what that does for cast metal casting in general, and the engineering that can go into it, right? So now we don't have to have these safety factors of these large gargantuan multi-ton castings, or larger than life needs to be for even for automotive castings and things of that nature. We can cast things once we have these things dialed in, and we get rid of the naysayers and the people that just don't believe that biofilm actually exists. We can engineer parts that are much smaller, much thinner, and they're much stronger. So we don't have to deal with any of those nuances of that safety factor that we traditionally engineer into castings because of the nuances of failure from tensile elongation and yield.
Yeah, you're absolutely right. And you see that particularly in aviation and very especially in helicopters. And there, the helicopter drive shaft system must not fail. If it fails, you're in deep trouble. And of course, it is the thing that fails very often and brings the helicopter down. And there, the safety factor is about a factor of 5 normally. And that's a big factor when you think that if we had good metals and they didn't need a safety factor, they were just strong enough to hang on and do their life job without fracturing, the helicopter would weigh a fifth of the weight that it does. I mean, it's a fairly mind-blowing concept to apply.
Well, this is probably a great place for us to wrap up this conversation. It's been it's been fabulous for me.
Mm,
I hope for everybody else as well.
mm.
But Professor Campbell, thank you so much for coming on. Thank you for your time. It's just been an honor, and I'm left with a lot more questions. So hopefully you'll be amenable to doing this again sometime, and we can have another conversation.
Well, thank you for the offer to join you. I'm always keen to promote good casting technology, and the more of us that get it, the better our industry will be, and we might be able to charge decent prices for our castings.
There you go. Make a living at it, huh?
Yes, yeah. We'll all be able to sleep better in our beds. Yeah.
Absolutely. Thank you very much, Professor Campbell. It's been a pleasure.
Okay. Well, I'm very happy to have been, and again, thank you for the offer.
Thank you. Thank you.